All right, well, thank you very much. Yeah, I'll just tidy this up. So after yesterday's sort of survey, we've laid the foundation for some more technical talks, hopefully not too dense. And the room's thinned out a little, which is great. So what I'd like to do today is describe in some detail recent work on gluing periods for DHT mirrors. You can find this on the archive at 1910-11955. And this is joint with Fenglong Yu and Jordan Kostiuk. Coincidentally, Fenglong is actually in the UK right now. He's in Birmingham today. So there you go. What it's worth. All right. So, and again, the theme is basically gluing periods for DHT mirrors. All right. So I talked about two motivations last time. The motivation number one came from sort of the traditional Calabi-Yau mirror story. Okay? And that was the idea that if you have a Calabi-Yau n-1 fold sitting in a Calabi-Yau n fold, that this defines a fibration of the Calabi-Yau n fold by Calabi-Yau n-1 folds over P1 containing that specific Calabi-Yau n-1 fold as a special fiber. And the question that's natural to ask is, how are the mirrors? Oh, I don't know. I'll use a check mark here. So Calabi-Yau n-1 check. That's the mirror of the n-1 fold. And Calabi-Yau n check related. Okay, so that's the actual question there. The second motivation comes from the Landau-Ginzburg-Fano mirror correspondence. Now, at dinner last night, Alan ribbed me for not actually giving technical definitions in my talk. So I'll give the technical definitions today. All right. So the mirror to a quasi-Fano n-fold, QFN, let's call it, okay, is a Landau-Ginzburg model. Okay, so I have to define both of those. So what's a quasi-Fano? So a quasi-Fano is going to be a smooth projective variety whose anticanonical linear system contains a Calabi-Yau manifold and such that HI QFN O QFN equals 0 for I greater than 0. Is it okay, Alan? Thumbs up. Okay, very good. So what I said the other day, what I said yesterday was you should think of, okay, it was a colloquium style talk, right? Think of, okay, in dimension 2 would be the blow up of a del Pezzo surface, which is itself Fano, right, at points on E, where E is the anticanonical elliptic curve in the del Pezzo. Or you could think of the blow up of a Fano threefold along curves on its anticanonical K3 surface, etc. Okay, in practical terms, that's what you should think of. All right, and the DHT conjecture gives a way of linking these two motivations. Okay, so Yeah, so a smooth projective variety is anicanonical linear system contains a Calabi-Yau manifold and this cohomological condition hi of the quasi-Fano, O quasi-Fano is 0 for I greater than 0. Yeah.
What's the E in the delta?
Oh, this is the anicanonical E? Yeah, and that's the anicanonical K3. Yeah. So, so DHT links these two, okay? These two motivations, okay? And on the Fano side, the idea that one keys off of here is due to André Turin. So it's the notion of a Turin degeneration. Okay, so what's a Turin degeneration? So this is a degeneration V over the disk of Calabi-Yau manifolds over the unit disk delta NC, such that the total space script V is smooth, and the central fiber is a normal crossings union. So there's a normal crossings union, x1 union over z, x2 of two quasi-Fano varieties, x1, x2, that meet normally along a smooth variety Z, with Z contained in the anicanonical linear system of each. Okay. Now, it's nice to think of these in terms of Turin degenerations, these Turin generations showing up, if you start with a Calabi-Yau. Okay? So if your starting point is a Calabi-Yau, you can ask, oh, do you have a degeneration of this type? Fine. But you could run it in reverse. And in some sense, it's almost more informative to run it in reverse. So the reverse of a Turin degeneration is what I'll call a Kawamata-Namakawa smoothing. Okay? Yes?
If Z is in minus K x1, say, then doesn't that mean that the normal bundle of Z and x1 is nothing?
Normal bundle.
Intersection. It's the restriction.
Make sure I understand what you're saying.
And then the normal bundle is just Z.
Yeah, but I had to blow up, right? I mean, it's quasi-Fano.
Oh, I see. It's a blown up thing.
Yeah, it's quasi-Fano.
It's not, I see, quasi.
But this is exactly a good point. So this is a great point. This is why, what I'm about to do with the smoothing, if I set this up as two phonos intersecting on their common anticanonical, I can't do it. Right. Okay. So, yep, no, that's a good, great question. All right. So now let's do it the other way. Okay. Let's assume Z is smooth, and in both minus kxi. Let's assume that di are classes in pic of xi, such that both di restrict to the same ample class d in pic z. Okay. We'll let x1 union z x2 be as before, a normal crossings intersection of the two. All right. And then we say x1 union z x2 is smoothable to a Calabi-Yau manifold V if there exists a complex manifold script V with a map psi V to the disk such that psi inverse of 0 is the central fiber normal crossings, and psi inverse of t is a smooth Calabi-Yau for all t in the disk minus 0. All right. So if I denote now by Roman V general fiber of script V, then what Kawamata and Namakawa showed, among other things, is that x1 union over zx2 is smoothable to a Calabi-Yau manifold B if and only if the relative normal bundles of z in x1 and z in x2 are inverses of one another. It's okay if they're both trivial, but that's a special case. And secondly, and this is important, that the Calabi-Yau V is unique up to deformation of complex structure. All right. Good. So this is terrific. This tells us that if we have a pair of quasi-phonos intersecting on a common anticanonical, we can run the Kawamata and Namakawa machinery and smooth it out to a Calabi-Yau. And this is effectively what Turing called constructive or constructible Calabi-Yaus. In his very last paper, it was published posthumously in the Fano Memorial Proceedings. And it was also in that paper that he asked this question about, gee, given that this construction exists, and given that there's a notion of mirror symmetry for Calabi-Yaus and mirror symmetry for Fanos, might there be a connection between the two? And he didn't spell it out any more clearly than that. So in some sense, what DHT is doing is it's providing an answer to Andre Turin's question. Okay, so now let's move to the Landau-Ginzburg models. So an LG model of a quasi-Fano variety is a pair YW consisting of a Kähler manifold Y, to be of more chalk, such that H1 of Y equals 0, and a proper map W Y to C, known as the superpotential. Okay, note Y is non-compact, right? But we usually assume that it's compactified fiber-wise relative to the superpotential. Okay, and when that happens, those fibers are going to be of Calabi-Yau type. Yeah. Yeah, this is just, that's what I mean. Yeah, I think that's right. All right. So in its original formulation, in our paper in the String Math 2015 proceedings where we announced it, this gluing splitting conjecture says roughly that the LG models of Xi with superpotentials Wi can be glued in the symplectic category. I'll say what I mean in a second about that. Okay. So in particular, what I mean is that the monodromy symplectomorphism on Wi inverse of t for t a regular value of Wi associated with a small loop about infinity can be identified under mirror symmetry with the restriction of the Serre functor of bounded derived category of coherent sheaves on xi to bounded derived category of coherent sheaves on z. Yeah. Okay. What does that mean? Well, the Serre functor is tensoring with omega xi d, and the shift is by the dimension of xi. Right. So the motivation here is bounded derived category, so B-model story on the Turing degeneration side. Okay. Well, because this is referring to the Landau-Ginzburg model. So if you go all the way back to Kontsevich's first paper on mirror symmetry, monodromy on the B-model side is related to autoequivalences of the derived category of the A-model side. So he did this with the quintic, right? And you got the monodromies about 0, 1, and infinity in the quintic mirror derived from this equivalence. And this is the first evidence for HMS. Well, I'm not doing anything here other than say that under the mirror correspondence for HMS, right?
It seems to do something. I mean, so this monodromy, I assume, is something I think of as monodromy.
Yeah. So the monodromy, you should. So let's think about it as. Let's go back to the quintic and quintic mirror. Okay. So if we're talking about a quintic hypersurface, you have certain natural autoequivalences of the bounded derived category. And they come from such things as tensoring with omega and what have you, okay, Fourier-Mukai transformations. Each of those, in Kontsevich's formulation, corresponds to in the symplectic sense, a monodromy in a family of quintic mirror Calabi-Yau threefolds.
The word correspond is kind of a weasel word.
It's a total weasel word, which is why it's taken 20 years to develop the theory.
Okay, so there's not a functor, but there's a
No.
weasel.
There's a correspondence between operations. Yeah, that's right. Okay. And again, this is motivation. This is sort of observational motivation for the statement. Right. Okay. This is not part of a theorem. Well, in examples it is. Okay. So then up to a choice of a shift by dim xi, the action of monodromy on Wi inverse of t, according to this HMS-style philosophy, should then be identified with the autoequivalence of dBz induced by taking tensor product with omega xi restricted to z, which is in z inverse. Okay. So again, to anyone who's read Kontsevich's original paper, this is very familiar. This is simply and in fact, this is in some sense the motivation for his generalizing from that paper, which was talking about compact Calabi-Yaus, to the more general setting of Landau-Ginzburg models. Okay? All right, so there's no particular surprise there. I'm going to be deliberately switching them in a minute, okay? But right now, as a motivation for the original conjecture, we were very much thinking of the category of the boundary category coherent sheaves on the Turing generation side. Therefore, symplectic category, hence monodromies, on the other side. But it's a great question, and I'm about to switch it up. Okay? All right. So you now apply the Kawamata-Namakawa criterion, which says that nzx1 tensor nzx2 is OZ. So you get phi 1 for a clockwise loop around infinity on omega 1, W1 inverse of t should be the same as phi 2 inverse for a counterclockwise loop around infinity on W2 inverse of t. Okay? And so this suggested the topological gluing Pardon? Oh, did I change the notation? No, this is the monodromy symplectomorphism. I might not have introduced the notation. That would be the problem. How about phi I? Okay. Yeah. So this is what suggested the topological gluing, this sort of in this symplectic side topological gluing, in the original conjecture, in the original paper on DHT. Okay. Now, I should say, this is not without serious teeth, okay? So you can do Euler characteristic computations about this gluing, and you check that everything matches perfectly, where the Euler characteristic flips the way it's supposed to. You can do refined Hodge number computations on both sides in large classes of examples, and everything checks, okay? So this is already really nice. But, and this is important, any good construction of mirror pairs should work, this is even if it's asymmetric, with the categories reversed. So the question is, how should gluing work with respect to complex structures? Okay? So now we're talking about the B model story on the Landau-Ginzburg side, on the fibration side. So we're talking about periods, if you like. Relative periods for Landau-Ginzburg models, that means periods for the fiber Calabi-Yaus. And for that matter, relative periods for the internal Calabi-Yau fibration, right, once you've glued them, and their relationship to periods of the total space Calabi-Yau as it moves in families. Because ultimately, that's the relation. You're moving up in dimension, okay? It's not enough to say that you have a relative B model story for the fibration on the Calabi-Yau. You need to have bootstrapped to the B model story for the Calabi-Yau itself. So this is the motivating question for today. Okay? All right. So I won't repeat the litany of cases in which we have established variants of DHT. We summarized that a bit yesterday. Suffice it to say, there's an enormous amount of evidence in favor of it, sometimes through making direct connection with other formulations of mirror symmetry, other times starting fresh. But for this particular question here, the key idea, which goes back 20 years to my PhD thesis, as it turned out, is the notion of a generalized functional invariant. Okay. So to explain what that is, let's go back to Kodaira's theory of elliptic surfaces and talk about the ordinary functional invariant. So Kodaira. All right. So Kodaira developed a theory of elliptic surfaces. He started with a one-dimensional base, and he focused mostly on a one-dimensional base. He called his basic theory, the theory of elliptic surfaces with section, the theory of basic elliptic surfaces. And the way he set this up is he introduced a pair of invariants for these families. So let script E be an elliptic surface, a family of elliptic curves. I could put any Riemann surface here, but I'm going to, for simplicity and for our applications, just put P1T, okay? Make it genus 0. This is not necessary, but I will. And of course, if you look at the multi-valued map from the base of this family of elliptic curves, because you're allowed to have bad fibers, to the upper half plane, the map sending T to, say, tau in the upper half plane, then of course you can compose this with the classical elliptic modular function, and you get the map to the J line. Okay, so this is, if you like, a P1, 2, 3 infinity orbicurve. Okay, 3 special points. Now, Kodaira's functional invariant is the composition of these two maps. It becomes just a rational function, script J of T. Okay, and it's what he called his functional invariant. Now, Kodaira's two invariants for basic elliptic surfaces, that is, elliptic surfaces with section, are the functional invariant and the homological invariant. Now, the homological invariant you can think of as R1 pi lower star or Z. I mean, you can formulate it however you want that way, or you can think of it as a certain amount of additional information layered on top of the functional invariant. It is exactly J invariant of the fiber. Because Kodaira called it differently. So, yeah, so again, I'm referencing Kodaira because this was the origin of this particular theory. Homological invariant, okay, I could write it as R1 pi lower star, as I said, of Z, but I don't want to. Instead, I want to tell you what the homological invariant tells you on top of the functional invariant that you don't already know. And the answer there is literally one bit of information for every singular fiber. And I literally mean a bit, okay? A plus or a minus, a 0 or a 1. What the homological invariant in the presence of the functional invariant tells you is whether the local monodromy about that fiber should be multiplied through by minus the identity or not. In his notation, it puts a star on the fiber. Okay? Okay, but if you make the further hypothesis that the surfaces in question are semi-stable, so all of their singular fibers are of type IN, not IN star, okay, then you can summarize Kodaira's observation about these invariants as saying, for semi-stable elliptic surfaces with section, isomorphism as elliptic surfaces is equivalent to having the same functional invariance. So under the right hypotheses, the perfect invariant for elliptic surfaces is the rational function. Okay? So what I want to do next is generalize this to K3 surfaces with a lattice polarization. By which I mean generalize the elliptic curve fibers. right? I don't mean look at elliptic K3 surfaces with section. That's a different story. But what I mean is generalize the fibers. Okay? So to do this, as we talked about yesterday, there's no one class of projective algebraic K3s to be considered. In fact, if I do 2n polarized K3s, I've got countably many 19-dimensional families of these, right? So you have to decide what you want to be the class of K3s that stands in for the elliptic curves in this theory. One thing I mentioned yesterday also was that the more you lattice polarize a K3, the smaller its moduli space gets in dimension. So a K3 surface that's lattice polarized all the way to rank 20 behaves like a CM elliptic curve, right? They don't come in non-isotrivial families. On the other hand, if I want to move in a one-parameter family, it's enough to restrict to the case where the polarizing lattice has rank 19. So that's what we will do. So we'll assume the K3 surfaces are lattice polarized by a lattice of rank 19. Okay? Oh, so yeah, I could give the formal definition, but it's going to take us a bit of field. All it means is, yeah, all it means is that with respect to a suitable marking, you are fixing a sublattice of the K3 lattice that always has to be in Nernst-Severi. So the rank 1 version of that is 2n polarized K3s. Yeah. Now there's some subtleties. So moving in families, there's a subtlety, right? That's fine for a single K3, but when you move in families, you have to ask how the local monodromies act, right? And so we're usually going to assume that the families are lattice polarized families, which means trivial action of monodromy on Nernst-Severi. Yeah. Okay. So specifically, I want to take, this is not the most general rank 19, I want to take the lattice to be m equals h plus e8 plus e8 plus minus 2n. Okay, so this is just 0, 1, 1, 0. These are the negative definite E8 lattices, right? The full K3 lattice is h plus h plus h plus e8 plus e8. So it's obvious that this does embed primitively, in fact, in that lattice. So that's great. These are nice. But this is not pulled out of a hat, okay? So I said that there was an extant form of mirror symmetry for K3 surfaces. That extant form of mirror symmetry, which goes back to at least Dolgachev, building on work of Nikulin and Pinkham, takes you from one lattice polarized moduli space, one lattice polarized family of K3s to another. So given one lattice, there will be another lattice that characterizes the family. This family, as you might guess, is characterized by the fact that under mirror symmetry, it's mirror to the 2n polarized K3 surfaces. Okay? So if I ask you, what is the mirror of a quartic K3? You can say, aha, yes, it is an M2 polarized K3. Okay?
Can you briefly say in which sense they're mirrored?
Briefly, very briefly, very briefly. So global Torelli and surjectivity of the period mapping work not just for polarized K3s, but for lattice polarized K3s. Okay? The existence of coarse moduli spaces, which are arithmetic quotients of type 4 symmetric domains, that all goes through. So if you're supposed to match one family to another family, all you need to know is how to pass from one lattice to another lattice. Okay? And this is what Dolgachev formalized in his paper from, I saw him give a talk on it in '95 in Santa Cruz. He had the algebraic geometry AMS event. But at sometime in the mid-'90s, early mid-'90s, he wrote this paper. And there's a lot of subtleties, but roughly speaking, under the right conditions, it's nothing more than saying you take your polarizing lattice sitting inside the K3 lattice, you find another copy of H that serves as a pivot, right? And then the complement in the transcendental lattice turns out to be the new Nernst-Severi lattice. Okay. So that's sweeping all the details under the rug. All right, but here it's abundantly clear that what I just said works. Okay? There's your 2n and your minus 2n. There's another copy of H. Fine, we're good. Okay? So the statement here is that if you want to know how to characterize lattice theoretically, the mirror family of K3s to a 2n polarized K3, it's this polarizing lattice. Okay, very good. So how about the rest of the story? Well, obviously, for Kodaira's theory, you need the J line to generalize. So let's just think for a second about what this picture would look like. So I need the J line, which is H mod PSL 2Z, to somehow correspond to a moduli space of Mn polarized K3s. Okay, well, I mean, roughly speaking, that's clear. It's going to have to happen. Is this the right thing? Well, I told you this has to be one-dimensional. I told you it has to be an arithmetic quotient of a type 4 symmetric domain. Well, what are the type 4 symmetric domains in small dimension? Well, in this case, in small dimension, it's isomorphic to H itself. By H, I mean the upper half plane itself. So I'll step you through this quickly just because it's fun. The rank here is 19. The total rank of the K3 lattice is 22. 22 minus 19 is 3. If I projectivize my 3 periods, right, integral over the 3 periods, I get three complex numbers. If I projectivize, that's a P2. That's not one-dimensional. What's wrong? Well, surjectivity of the period mapping is coupled with another condition on polarized K3s, periods, which is that they all satisfy a quadric condition. So you're actually lying on a conic in that CP2. Yeah, that's right. And then you have the positivity condition, so you're literally on the upper half plane. Okay? This is encapsulated representation theoretically by a symmetric square operation. So it's a beautiful elementary kind of observation. But the upshot is that you can think of this moduli space as a quotient by a group, okay, gamma something, I'll say what it is in a minute, okay? If we were working with the action of the full O plus of the transcendental lattice with integer coefficients on the thing of higher dimension, those coefficients in this matrix would be integers. But because of the symmetric square root operation, we're actually in the group gamma naught of n plus the Frick involution. In other words, this is tau goes to minus 1 over n times tau, which introduces a root tau in general when you write it out. Okay, so you're in PSL2R. Everything acts beautifully on the upper half plane, but you're not in PSL2Z. Okay, very good. So we have an analog for rank 19 K3s. What about the whole picture now on the left-hand board? Well, if I have a family of said K3s, say over a curve, you do exactly the same thing. Upper half plane. This is now the Hauptmodul P1, right? Instead of working with the Q series for the elliptic modular function J, you work with the Hauptmodul for gamma naught of n plus n, okay? But in any case, you quotient down gamma naught of n plus n, and the composition, once again, is a rational function, which we could denote Hn of t, and we call this the generalized functional invariant for Mn polarized families of K3 surfaces. Correct. So that's an assumption in what I'm putting here, but the only reason I'm doing that is because it's all I'm going to use for applications. Because if you have a K3 surface that's fibered, right, the base will necessarily have to be, I'm sorry, a Calabi-Yau threefold that's fibered, the base would have to necessarily be P1. But you're absolutely right. This goes on forever, and there's only finitely many cases that have genus 0. I forget, but it follows from a theorem of Ogg. Okay. It's even more restrictive. I'll come back and talk about this tomorrow. It's even more restrictive if you restrict yourself to the ones that actually can be the base of a family of K3s whose total space is Calabi-Yau. That I remember. So, okay. Now, I'll tell you later. I'm getting off track. So this is good. All right, and the technical point that was already brought up earlier in response to a question is that these are Mn polarized families, not families of Mn polarized. Families of Mn polarized would be allowed to have monodromy acting non-trivially on the polarizing lattice. Mn polarized families say the only action is basically on the transcendental lattice. Okay, acts trivially on the Mn part. All right, so a theorem which I'll say more about tomorrow with Harder, Novoselicev, and Thompson is the complete classification and construction of all Mn polarized K3 surface fibered Calabi-Yau threefolds. Okay. And just because it was asked, okay, you want to say something? Yes. Yes, I have to put I'm going to put a little comma here now because you finished it. Yeah? Okay. And you and Remke's finished it. But I thought you finished it with Remke's.
Yeah, we have restriction. We don't have the same kind of explicit description of which one.
Okay. Since I'm saying the full thing, I'm going to put parentheses here, and then I'm going to say n greater than or equal to 2. Then we're safe. Okay. So Alan has some work with Remke's Kustra, a former student of James Lewis. And they're addressing the n equal 1 case, which is extra subtle because of, well, a number of reasons, due to extra automorphisms. All right, but what I wanted to say here is that in terms of the n's that show up in this classification, okay, the only n's that show up under the assumption that you are a non-isotrivial fibration are n equal 2, 3, 4, 5, 6, 7, 8, 9, and 11. Did I get that right? I think I did. All right. And if you know something of Iskolsky's classification, this should ring a bell. Okay, so this is a good hint that it's playing well with phonos. All right. Okay. So, but what I really want to say today, because I'll come back to that theorem tomorrow, what I want to say today is just what goes into that theorem is a lot of Hodge theory and a lot of sort of delicate application of minimal model program to sort out all of the cases where the Calabi-Yaus are smooth versus singular of various sorts, a generalization of Kodaira's classification of bad fibers of ADE type to the Mn polarized case. There's a lot of work that goes into it, but if you focus on the underlying Hodge theoretic aspects, what you see is that the classification, not the construction, reduces to knowing and studying the generalized functional invariance. So the way to think about this is you're controlling the periods of the resulting Calabi-Yau threefold by controlling the fiber-wise periods of the K3s relative to the map to the base. That's the rough idea, okay? And since the description of your family of K3s, whose total space is going to compactify to a Calabi-Yau threefold, is entirely dictated, except for the bad fibers, which don't affect periods, right? Is entirely dictated by the choice of this rational function, then really it's the behavior of the rational function relative to the orbifold structure of the modular curve that dictates everything, okay? Or if you want to soup that up, consider a local system on the modular curve that stores the relevant data of the periods in that family, and you have to adjust your ramification behavior accordingly with respect to that local system. Okay, so that's very roughly what's going on there. But what's the upshot? So at least for threefolds coming from Mn polarized families, knowing the generalized functional invariant map to the moduli space of Mn polarized K3s fixes the geometry of the total space. So this suggests something very nice. It suggests that the DHT gluing must amount, this is in the complex category on this side, to gluing, whatever we mean by that, of the generalized functional invariance of the two LG models to produce the generalized functional invariant of the K3 fibered Calabi-Yau. All right, so if I give you two rational functions, what is the simplest and most natural way to combine them to get a third rational function? Okay, now having said this, there's no unique answer to this question. I know of at least two reasonable answers, okay? But the correct answer here is multiplication, okay? So the answer in simplified form is multiplication of rational functions. Okay. It doesn't get any easier than this. This is gluing, right? All right. So I'm going to illustrate this with the case of quintic Calabi-Yaus. And this is not the only way to get this answer. I'm going to pick a particular Turing generation. I'm actually going to achieve the quintic Calabi-Yaus through a geometric transition from conifold. Oh, didn't I do that? I see. Okay, I'll start here. So I mentioned earlier that it's easier if the relative normal bundles are trivial. And that's actually the case where this naive multiplication of rational functions argument is going to work spot on. So let me illustrate it with that case and then explain how you can go from that to the quintic mirror, which is a little bit more subtle. Yeah, so I'm not assuming that because I'm not using the classification result in the way, I'm not using the classification result for anything about, the heuristic would implicitly be assuming that, and that's why it's a heuristic. Okay, yeah. Because there's examples I'm going to give where it won't. No, absolutely, it's good. Yeah, I'm trying to connect dots ex post facto that make it easier to read the paper. Okay, so let me illustrate with the case of quintic Calabi-Yaus. Okay, and I'm going to do that, as I said, not by starting with quintic Calabi-Yaus. Quintic Calabi-Yau would have H11 equal 1. Now, H11 equal 1 is going to end up giving us those relative normal bundles that are non-trivial, and it's going to be easier in the case when they're trivial. So what we're going to do is we're going to transition through a conifold transition. I'm going to write down a complete intersection Calabi-Yau, which has H11 equal 2, which is what you get by going to a certain conifold locus of quintics containing a plane, and then doing a small projective resolution. Okay?
So now in dimension 3.
Yeah, let's do dimension 3, but I don't have to. I mean, our paper is, yeah, sure. Yeah, I want to do dimension 3 because then I get to make specific reference to the MN, and in fact, I'll do M2. Okay? Okay, so let's consider Q5 tilde. It's a complete intersection of by degree 4, 1, 1, 1 in P4 cross P1. Okay, so as I said, this is the conifold transition of the quintic that was studied by physicists, ages ago. So it's a conifold transition of the quintic threefold in P4. This admits a nice Turing generation. So Q5 tilde has a Turing degeneration to x1 union over K3 x2. And this K3 here, well, you can already guess from the 4 there. Right. This is going to be a quartic K3. Okay? So, of course, its mirror is going to be M2 polarized, in the sense we've been talking about. Now, what are x1 and x2? Well, x1 is 4,1 in P3 cross P1, which is a blowup of P3 along a complete intersection of two quartic surfaces. And the x2 is a 4,011 in P4 cross P1, which is the blowup of a quartic threefold along a complete intersection of two hyperplanes. Okay? So why do we want to do this? Well, the reason we want to do this is that we need to make contact with somebody's theory that tells us how to describe the Landau-Ginzburg model, right? Because our quasi-Fano, so they're not even Fano. You can't even say, you know, go to somebody's list of Fano threefolds and the ones they've constructed. So, for instance, there's a marvelous group in London here that's been working for a number of years. It's London and other places, but I mean, I think of London as, well, London's the center of everything here, isn't it? But I think of it as centered at Imperial, at least from across the pond. And what they've been doing is using mirror symmetry for Fano varieties and the corresponding Landau-Ginzburg models to develop general tools to deduce the existence and properties of Fano fourfolds, and higher in principle. And it's a wonderful program. They've made great progress. And Ilana Kalashnikov is at Harvard, and we were talking all the time, and she's part of this. But what's useful to us is that as a side effect of this program, they developed general tools for passing from suitable classes of not just Fano, but even quasi-Fano varieties to their Landau-Ginzburg mirrors. For the purposes of this discussion, we can use an old tool of Giventhal, and it just goes by the name Giventhal's formalism. So Giventhal's sort of toric formalism gives us the LG mirror of Q5 tilde, X1 and X2 explicitly. Okay, so we'll give names to the mirrors. We'll call them Q5 tilde check, X1 check, and X2 check. Okay. Yes?
Possibly getting the P1 as a conic in P2 and degenerating it to two lines?
That might be a good way to think about it. Yeah, that might very well work here. Yeah. But if you do more general quasi-Fanos, you don't expect, yeah. Because once again, this is that case where the relative normal bundles are both trivial, so you can get away with a lot.
They are trivial.
Yeah, in this case, yeah. Which is why we're starting with it. Okay, so just, I mean, again, this is not because I expect it to all be edifying, but just so you can see how concrete what we're talking about is. You apply Giventhal's machinery, and you get that Q5 tilde check is the compactification of, okay, so then it's X1, X2, X3, X4, Y in a big torus C star to the 5, such that X1 plus X2 plus X3 plus Q1 over X1, X2, X3, X4 plus Y equals 1. And X4 plus Q2 over Y equals 1. Okay. Notice the two parameters here, and these are corresponding to the two complex structure parameters of this mirror Calabi-Yau. Because up there, Q5 tilde is actually H11 equal 2, so this had better have H21 equal 2. Okay, there we go. There's the parameters. LG for X1 is given by superpotential W1, X1 check to C, sending X1, X2, X3, Y1 to Y1. And X1 check is the fiber-wise, relative to this W1 map, compactification of X1, X2, X3, Y1 in C star to the 4th, such that X1 plus X2 plus X3 plus and then this is our notation, so I'll stick to it. Q11 over x1, x2, x3 plus Q01 over y1 equals 1. Okay, and similarly for x2, I can write it out if people want, but maybe that's not edifying. Okay, so the main point here is that we have an explicit mechanism for accessing the Lambda-Ginsburg models. And we can get away with this as long as our quasi-Fano varieties can be realized as complete intersections and toric varieties. All right, so how do we see the quartic mirror, so M2 polarized fibrations? Well, okay, let's take x1 check, for example, and we'll do a change of variables. So xi tilde is xi over 1 minus q01 over y1 for I equal 1, 2, and 3. Okay, and then lambda 1, so that's the generalized functional invariant for this family, just becomes q11 over 1 minus q01 over y1 to the fourth. Okay, so this is really kind of marvelous because your Lambda-Ginsburg model now has two free parameters, and one of them scales the target, so which is scaling the modular curve, and the other is clearly related to the value q01 on the base. Okay? So done right, you can directly reinterpret the natural complex structure moduli associated to the Lambda-Ginsburg models cleanly in terms of the fibration, in terms of the internal fibration, keeping track of where certain bad fibers are and what have you. This is the thing I said. Do you want me to write it down? I'm happy to.
No.
Yeah. So, no, it's not there. I will insert it later if you really want to see it. This is x1 check looking at the internal fibration. So I can step away from x2 check, do this computation, and then I can give you x2 check if you'd like to have completeness in your notes. Okay. So what I'm doing here is I'm changing variables so that you can actually see the quartic mirror family show up. You see that x1 tilde, x2 tilde, x3 tilde, x1 tilde plus x2 tilde plus x3 tilde minus 1 plus lambda 1 is 0. That's the affine form of the quartic mirror family. Okay? It's Giventhals' way of writing it down. So as I said, the generalized functional invariant then for x1 check, comma, w1 is that. Okay? So it doesn't get much simpler than this, where you have two parameters. One is just scaling the rational function, and the other is basically telling you the position of some bad fiber. Okay, so Spencer asked, so I'm going to quickly put it up, the LG model for x2, just so that notes can be complete. But I'm almost out of time, right? Yeah, so Spencer, can I not put it up? Okay, there you go. So I won't put it up. So what I will do, since I'm almost out of time, is get to some punchlines. I think I've sprinkled punchlines throughout, but let me give you another one. So how does gluing work? So gluing, and again, you have to assume I wrote out the answer for x2, but it's all in the paper. q1 equals q11 equals q12, q naught equal q naught 1, y equal y1 equal q naught 2 over y2. Then, if lambda is the generalized functional invariant for the internal fibration on q5 tilde check, then lambda over q1 is lambda 1 over q11 times lambda 2 over q12. Okay, so gluing is multiplication of rational functions. Okay? Now, because I want to state, a more interesting punchline than that, let me just say, you then can compute the periods using the generalized functional invariance, the actual periods, and the Q series for the periods, if you like, for the relative periods, the fiber-wise periods of the Lambda-Ginsburg models, the two Lambda-Ginsburg models, the fiber-wise periods of the glued Lambda-Ginsburg models, and the periods of the resulting family of Calabi-Yau threefolds. And theorem, the holomorphic periods of LG models are related by gluing and integrating out the base to those of the Calabi-Yau threefolds. I called it Q5 tilde check. And without saying what these are, other than saying that they're holomorphic periods that you can write down, Q1, Q naught, Q1, F naught, K3, Q1 is 1 over 2 pi I integral F naught x1, Q1, Q naught y, Q1, F naught x2, Q1, y, dy over y. So the base parameter for the internal fibration by M2 polarized K3s on the Calabi-Yau threefold is y, which has been identified by gluing the base parameter for x1 Lambda-Ginsburg model to the x2 Lambda-Ginsburg model with a suitable relative scaling. That's y. But I want to integrate it out to get periods for the total space. And this is the formula, and this star is the Hadamard product with respect to this Q variable. Thank you. Yes?
I was just curious if there is anything to be said about the Gauss-Lane
Yeah.
Picard-Fuchs.
Absolutely. So this is a statement about holomorphic periods. In fact, we have a corresponding statement about the entire I function. And the I function, in the sense of Giventhal, is just another way of saying the basis of solutions to the Picard-Fuchs equation. So on the level of Picard-Fuchs equations, you can rewrite this in many cases just as a clean kind of a middle convolution operation relating the two. And just because it's so cool, and I have to mention it, you can apply this kind of trick where you're looking at the internal fibration by K3s in many cases, but you can also apply it. I didn't do it here for the quintic mirror. I did the fibration on the mirror of the conifold transition of the quintic. But I can change variables and then restrict to a sublocus in moduli and recover the quintic, which means the M2 polarized fibration then gets induced on the quintic mirror. Okay, so note, in the original paper by Candelas, De La Osa, Green, and Parks, there was a mysterious, or a surprise, I guess they called it, that came up when they were computing the period for the very first time for the quintic mirror, okay? And the nature of the surprise was that they had simplified their variables down a bit, done some computations, and in the last step, out popped a 4f3, 1/5, 2/5, 3/5, 4/5. Okay, I workshopped that paper for a mirror symmetry class in the spring, and nobody bothers looking at this argument anymore, because as soon as that paper came out, Dave Morrison came out with his paper, which said, oh, these are just Picard-Fuchs equations, here's Griffith's Dwork. But when I workshopped the paper, I realized you go back to the paper itself, and the change of variables that they did was identifying an internal quartic mirror fibration on the quintic mirror. So the explanation for the original formula, derivation of the original formula for the holomorphic period for the quintic mirror in the classic paper is actually using this internal fibration. Okay, so it's a very cute and cool historical note, and I wonder if the field might have developed differently if people had realized that early on. So anyway, thank you. Yeah.